Hello math people. In this video I just wanted to go over section 2.5, which is zeros of polynomials. So our objectives for today, see spoilers, are to classify the different types of zeros, to apply the rational zeros test, to use synthetic division, which you see down here, to test and factor out known zeros, to identify complex conjugate pairs, and to write the equation of a specified polynomial using the linear factorization theorem. So, recall from section 2.4, which was dividing polynomials, that we can use synthetic division with a zero to factor out that zero term out. So because 2 is a zero of x cubed plus 5x squared minus 2x minus 24, we can factor out an x minus 2 term. And let's go ahead and try that right here. So we're going to write the coefficients in order and using placeholder zeros if needed. So 1, 5, negative 2, negative 24. And then we're going to place our 0 out here on the left, so that's 2. And we're going to bring 1 down and multiply by 2 to get 2. And then we're going to add this to 5. And yeah, we're going to add this to 5 to get 7. We're going to multiply that again by 2 to get 14. Add that to negative 2 to get 12. Multiply that by 2 to get 24. And of course this equals 0. And that's what we want, so that we are able to factor it out. Right? We want a 0 remainder. And so this means that x cubed plus 5x squared minus 2x minus 24 is going to be equal to our factored out term, so x minus 2, times the quotient. So that's x squared plus 7x plus 12. And what we're going to use a lot in this chapter is then further simplifying this. So we can use any regular factoring methods that we want to realize that that second term is going to be what two factors of 12 add up to 7? That's going to be 3 and 4. So x plus 3 times x minus 4, or x plus 4, excuse me. And so that means our zeros are going to be 2, negative 3, and negative 4. Now let's talk about the types of zeros real quick. So we have the real zeros. Those are rational and irrational zeros. So rational zeros may be some factors like 2x minus 1, where the 0 is 1/2, or x minus 3, where the 0 is x equals 3. But we can also have irrational real zeros, such as x squared minus 2, where we're going to have plus or minus the square root of 2 as zeros, right? Our third type of zeros are going to be the complex imaginary zeros. So, for example, the equation x squared plus 1 has plus or minus I as a 0, right? Or x squared minus 2x plus 2, we can use the quadratic formula there to find out that 1 plus or minus I are zeros. With that in mind, let's talk about rational zeros. So that first type of zeros that we have here. The possible rational zeros of a polynomial, a n x to the n plus a n minus 1 x to the n minus 1 plus so on, our usual polynomial notation, plus a1x plus a naught, are going to be any factor of a naught divided by any factor of a n. So what that means is we'll do an example. So we're going to list the possible rational zeros of x cubed plus 2x minus 12. And we only have to think about the leading coefficient and the constant term. So the factors of the constant term of negative 12 are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and I'll just let you see that equation again, x cubed plus 2x minus 12, plus or minus 6, plus or minus 12. Right? And then the factors of our leading coefficient, positive 1, is just going to be plus or minus 1, right? And so this gives us the possible rational zeros of plus or minus 1, plus or minus 2, plus or minus 3. It doesn't change it because it's just plus or minus 1 in the denominator, so we can actually just write it like this. And these are the possible rational zeros. And that makes sense because if we have these linear terms, x minus c1, x minus c2, so on, we're going to want c1 times c2 all to multiply together to be negative 12. So it has to be factorable, if that makes sense. Our next example is listing the possible rational zeros of 5x to the 4th minus 3x cubed plus 2x squared plus 7x minus 14. And again, we only have to consider our leading coefficient and our constant term. The factors of our constant term, negative 14, are plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. And then the possible, the factors of our leading coefficient 5 are just going to be plus or minus 1, so this one remains unchanged, or plus or minus 5. So all of these divided by 5. So another example. well, let's list the possible rational zeros of x cubed minus 6x squared minus 9x plus 14, and then let's find all the zeros, okay? So first, I'm going to list the possible rational zeros. So we know that they're going to be plus or minus 1, plus or minus 2, plus or minus 7, or plus or minus 14, right? There's nothing else that they can be. Rational. So of course we could have irrational zeros maybe, but for this term, let's just check all of those zeros. So I'm going to put this equation right here into my y equals on my calculator. So we have x cubed minus 6x squared minus 9x plus 14. Now I'm going to go to my grapher and I'm just going to check off all these values. So I'm going to start my graph, and I actually see that 1 already is a 0. So I can list off 1 as a 0. So one of the zeros occurs at x equals, I'm going to spell that right. One of the zeros occurs at x equals 1, right? So my next step is actually going to use synthetic division to factor that out so that I can get a new polynomial that I can maybe factor better. So let's try that now. So as always, going in order and using placeholders if needed, we have our coefficients 1, -6, -9, and +14, and our 0 is 1. So we're going to bring down this 1 to 1, multiply by 1. We're going to get -5 here. We're going to get another -5 here. This is going to add to -14. That's going to go up to -14, and we have 0 as we wanted. And so we're going to factor this out. So we're going to factor out an x minus 1, because that's what's going to be our 0 term. And then our polynomial is going to become x squared minus 5x minus 14. And again, what are two factors of -14 that add to -5? I'm going to say this is equal to x minus 1 times x minus 7 times x plus 2. And if you need a recall on factoring, I have some videos in this playlist as well. And I also shared one on the Canvas announcements. And so this is going to suggest that the zeros are 1, 7, and -2. And you can probably check for yourself that those all indeed are the zeros. And since it's a degree 3 polynomial, it's all of the zeros. And we have found all of the zeros. One more example, we're going to find all the zeros of 2x to the 4th plus 7x cubed plus 11x squared plus 28x plus 12. And so our factors are going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, and then all over either plus or minus 1 or plus or minus 2. So again, you would put this in your calculator and you would start checking. So I'm going to put 2x to the 4th plus 7x cubed plus 11x squared plus 28x plus 12 into my y equals. And then I'm going to check my table, and I'm going to find that -3 is a 0. So -3 is a 0, and we just checked that. So I'm going to factor that out using synthetic division, and that's going to be our next step always. So once you find a 0, you're actually always going to want to factor it out with synthetic division, because that's going to simplify your polynomial quite a bit. And so we're going to get 2, 7, 11, 28, 12. This 2, bring this down. We're going to multiply by -3 to get -6. Add those up to get 1. Multiply by -3 to get another -3. Add these up to get 8. Multiply by another -3 to get -24. Add those up to get a +4. And then multiply again by -23 to get -12. Again, this factors well because we have a 0 remainder. And so we get x plus 3, because -3 is a 0, times 2x cubed plus x plus 8, plus x squared plus 8x plus 4. All right. Now, let's see if we can factor this further, and I think we can. So I'm going to start grouping in this one. So let's group these two terms together and these two terms together, and I can pull I'm going to write this here. I'm going to pull an x squared at this term, and we're going to get 2x plus 1. And then I'm going to factor out a 4 from this one, and I'm also going to get 2x plus 1. Now we can factor out this common term inside of here, and we're going to get x plus 3 times 2x plus 1 times x squared plus 4. Is that correct? Yeah, and so this is going to suggest that excuse me, I'm going to check this one moment. So negative 1/2. Yeah, and so we still want to find all the zeros. Okay, so this tells us that x equals a negative 3 is a 0, which we already found. This tells us that x equals negative 1/2 is a 0, which we found. And then we're going to have to do a little bit more work with this one, right? So we have x squared plus 4 equals 0, means that x squared is equal to negative 4. And this only happens when x is plus or minus 2i. And so that's all our zeros because this is a degree 4 polynomial. So our zeros are x equals negative 3, x equals negative 1/2, and x equals plus or minus 2i. And that's how we found that out. You're going to have an example like this in Pearson, and I hope that this has provided some insight on how you do it. Basically, step 1, use the rational zeros test to try and find all the possible zeros it could be. Test those in your grapher, and once you find one, you're going to want to put that into synthetic division. And then you're using that, whatever's left, you're going to try to factor that and see if you can get anything out. And remember, we have 3 types of zeros. We have real zeros, which are the ones you're used to, and we have imaginary zeros. So x squared plus 4, which gives us plus or minus 2i as the zeros. Those are imaginary, and you have to watch out for those. So our next topic is going to be complex conjugates. So if a plus bi is a 0 of a polynomial, then so is a minus bi. And this is always true. And you can see it here, x plus or minus 2i. Or in this one up here, where we have 1 plus or minus I, or plus or minus I. Anytime you see an imaginary 0, it comes with a pair. So just a short exercise, find the complex conjugates of all of these. Like, do this on your own, and then I will just pause the video, and then I will start doing those myself. So this is 0 plus I, so the conjugate is negative I. 2 plus 3i, the conjugate is 2 minus 3i. 4 minus I, the conjugate is 4 plus I. Negative 2 plus 3i, the conjugate is negative 2 minus 3i. Negative 7 minus I, the conjugate is negative 7 plus I. And 1 minus the square root of 2i is going to be 1 plus the square root of 2i. Just make sure that you remember that whenever there's a complex root, there will also be the conjugate as a root. So our next, and I believe, so our next topic is going to be the linear factorization theorem, which states that for any polynomial, we can rewrite it as its leading coefficient times all of its zeros. So times a linear factor of all of its zeros. So let's just do examples. So all the CI are possibly complex and possibly repeated, and I will go into what that means. So our usual factoring, x squared minus 1, it's not repeated and it's not complex. We have x minus 1 times x plus 1, right? This is a nice one, and I like to start out with that one just because it introduces us to that. And that's what we've been doing this whole time, is factoring, right? Another example should be x squared plus 2x plus 1. And we did this one earlier here, so let's go up over here. We found that no. This is actually a perfect square, and I was wrong. So if we do the math here, we're going to see that 1 is a perfect square, x squared is a perfect square, and 2x is twice their product. So this is actually x plus 1 times x plus 1. So it's x plus 1 squared. And that's why I said it can possibly be repeated, right? So this is 2 zeros and they're repeated. And I just want to make sure that you realize that in this formula right here, the zeros can be repeated. Another example where it's going to be complex is x squared plus 1. That's going to be x minus I. So this is the 0 where x equals I. And then x plus I, the 0 where x equals negative I. Remember, because we're subtracting the 0. So x minus I and then x plus I. And you can also factor that out, expand that out if you want, to be kind of clear about that. And then 2x to the 4th plus 7x cubed plus 11x squared plus 28x plus 12. And that is actually this example right here that we did. And we found all of its zeros, and I'm just going to bring those up. So we found that the zeros were negative 3, negative 1/2, and plus or minus 2i. And what that means is we can write this as our leading coefficient 2 times x plus 3 times x plus 1/2 times x minus 2i times x plus 2i. And you can actually try this again as yourself as an example. Try to expand this, and you will see that it gives us back that exact equation. What this actually means is that we can write any polynomial we want if we know all n of its zeros and their multiplicities, all n of its zeros, or all of its zeros and multiplicities, and a single other point, right? And this is going to be in your Pearson homework. So writing equations of a specified polynomial. Example. So let's give the equation for a quadratic polynomial with a 0 at x equals -2 and 3, and where f of 1 equals 12. And so we're going to start out, we know this is going to be sum a times x plus 2, that first 0, times x minus 3, right? So, and now we want to try to find a, right? So we want to find the leading coefficient, and we're going to use the fact that f of 1 equals 12. So let's just plug in f of 1 here. So a times 1 plus 2 times 1 minus 3 is going to equal a, and then 1 plus 2 is 3, and then 1 minus 3 is -2, so their product is -6. And since f of 1 is 12, we know that means that a has to equal -2. And that is going to make it so that a times, so I'll just write that out here, -2 times x plus 2 times x minus 3. So when x equals -2, this term becomes 0, so it's a 0. When this term is 3, it becomes 0. And then when we plug in 1, we see that we get out 12. And so that is our equation. And if you want, we can also expand this out. So this is going to be -2 times x squared minus x, and then minus 6. So this is equal to -2x squared plus 2x plus 12. Isn't that wonderful? Another example, let's give the equation of the polynomial with zeros at x equals -1, 2, 1 plus I, and where f of 0 equals -4. So notice here that because we have 1 plus I as a 0, we're also going to get 1 minus I as a 0 because of the complex conjugate pairs. So we're going to get 1 minus I. And so I'm just going to start writing that out. So we're going to have a times x plus 1 times x minus 2 times x minus 1 plus I times x minus 1 minus I. And then since f of 0 equals -4, we can just turn x into 0. So we have a times 1 times -2 times -1 plus I times -1 minus I is going to equal -4, right? And when we expand out this multiplication, we get 1 times -2 is -2, or 1 times -2 is obviously -2. But what about these two right here? So let's just perform that multiplication real quick. So 1 plus I times 1 minus I is going to equal, and we can cancel out this negative because there's two of them, right? So if we multiply both of these together, we get 1 plus I minus I plus 1, which is equal to 2. And so this whole thing actually becomes -4. So a times 1 times -2 times another +2 equals -4a. And so we know that means a equals 1. And so right here, this is the equation for this polynomial right here. So some general tips and strategies for your homework. Step 1 is to find any zero using the rational root test and or your grapher. Step 2 is to factor out using synthetic division. And finally, your last step is to repeat until you can find the rest of the zeros. I hope this has been a little bit helpful, and good luck. Bye-bye.